At 36 kilometers above Earth, the sky is black. Not dark blue, not deep purple. Black. The sun hangs in it like a spotlight, and the horizon curves away from you in every direction, a thin blue line separating everything alive from everything that isn't. At this altitude, the atmosphere is so thin that if you stepped outside without a suit, you would be dead in under 2 minutes. Not from the cold, not from the altitude, from the physics of what your body does when pressure disappears. Here's why that matters more than you think. The human body is a pressurized system. Every cell, every blood vessel, every cavity in your skull operates under a precise atmospheric contract, roughly 101,000 pascals of pressure pushing inward at all times at sea level. You don't notice it because it's always been there. It's the background hum of being alive on Earth. Your body doesn't regulate against pressure, it regulates with it. Remove that pressure, and the contract breaks in ways that are fast, specific, and deeply strange. Let's start at sea level and climb, because the effects don't begin at the edge of space. They begin much, much sooner than you'd expect. At 2,400 meters, the altitude of many ski resorts, your blood oxygen starts to drop. The air contains the same proportion of oxygen as at sea level, 21%, but there's less air. Each breath delivers fewer oxygen molecules to your lungs. Your body compensates by breathing faster and by pushing your heart to pump harder. Most people feel this as a faint headache behind the eyes, a low-grade sense of effort. Some people feel nothing. Some people vomit. The difference comes down almost entirely to a single protein in your red blood cells, hemoglobin, and how efficiently your particular version of it binds to oxygen under reduced partial pressure. You are already at ski resort altitude, running a slightly different version of yourself. At 3,600 meters, the compensation mechanisms start to strain. Altitude sickness becomes a real probability. Your brain swells. Not metaphorically. The tissue physically expands as fluid leaks from vessels that are trying to compensate for lower oxygen by becoming more permeable. That's what the headache is. Neural tissue pressing against the inside of your skull. In severe cases, this progresses to HACE, high-altitude cerebral edema, where the swelling becomes bad enough to cause confusion, loss of coordination, hallucinations, and death. Mountaineers call the early symptoms feeling off. The problem is that feeling off at altitude is neurologically indistinguishable from the early stage of your brain being slowly starved of oxygen. Your impaired brain is the last instrument you should trust to assess whether your brain is impaired. At 5,500 meters, roughly the base camp of Everest, the atmospheric pressure is about half of sea level. Each breath delivers half the oxygen. Your body can live here, just barely, but only with significant acclimatization time and only by flooding your bloodstream with new red blood cells. Your kidneys detect the oxygen deficit and release a hormone called erythropoietin, EPO, the same substance that made certain cyclists famous for the wrong reasons in the 1990s. Your body, at extreme altitude, starts doping itself. The red blood cell count climbs, blood thickens, clots become more likely. The mountain is slowly trying to kill you through your own survival response. Now we go up further, past where any human has ever climbed without supplemental oxygen, past where weather systems form, into a region most people will never see from anything other than a window seat. At 12,000 meters, you are in the cruise altitude of a commercial aircraft. Outside that aluminum tube, the temperature is around -57 degrees Celsius. Pressure is roughly 19% of sea level. A human body exposed here without pressurization would lose consciousness in about 15 seconds. Not from cold, the cold would take longer. From hypoxia. The oxygen partial pressure is too low for hemoglobin to load at all. Your blood, no matter how fast it moves, cannot pick up enough oxygen to keep the brain online. Lights out. No sensation. No warning, just gone. This is the body stops fighting altitude, and altitude starts winning permanently. At 19,200 meters, we cross what aviation medicine calls the Armstrong Line. Named after Harry Armstrong, the U.S. Air Force physician who identified it in the 1930s. This is the altitude at which atmospheric pressure drops to 6.3 kilopascals, the vapor pressure of water at human body temperature. What that means in practice is almost impossible to believe the first time you hear it. Your blood begins to boil. Not from heat, from the absence of pressure. The dissolved gases in your tissues, nitrogen, oxygen, carbon dioxide, begin to form bubbles. This is called ebullition. The same process as decompression sickness in divers, but happening to your entire body simultaneously and with no way to reverse it. Your saliva evaporates off your tongue. Your skin swells. Your eyes begin to expand. Internal cavities, sinuses, lungs, intestines, inflate as trapped gas expands by a factor of 6 or more relative to sea level volume. You do not explode. The skin is elastic enough to contain the expansion, just barely. But you inflate, visibly, grotesquely. And while this is happening, you are already brain dead from hypoxia, and you are already freezing, because the thin air conducts almost no heat and your body's core temperature begins dropping within seconds. Nobody has ever crossed the Armstrong Line and come back to describe it without a pressure suit. 2 people have accidentally experienced near Armstrong conditions and survived to give testimony. Both were test pilots. Both reported the same thing, a sensation of water boiling on their tongue, because it was, followed by immediate unconsciousness. They remembered nothing after that. Recovery was only possible because their aircraft was recovered and repressurized within the few seconds their brains had before irreversible damage. A few seconds, that's the margin. Now let's go to the edge of space, the Kármán Line, 100 kilometers. Here, the atmosphere is so thin, it is functionally indistinguishable from vacuum for most physiological purposes. Temperature swings from -70 Celsius on the night side to over 120 degrees Celsius in direct sunlight within a single orbit. There is no convection, no air to carry heat away from your skin, which means in sunlight you cook from radiation with no mechanism for cooling. In shadow, you freeze at the same rate. Unprotected skin exposed to solar ultraviolet at this altitude receives a radiation dose in minutes that would take years to accumulate at sea level. And radiation doesn't stop at UV. Cosmic rays, high-energy particles fired from distant supernovae and active galactic nuclei, stream through the upper atmosphere at near light speed. At sea level, Earth's magnetic field and the atmosphere itself deflect most of them. At 100 kilometers, you are outside most of that protection. A single heavy cosmic ray particle passing through your skull deposits enough energy in a narrow track to damage DNA in every cell along its path. Astronauts on the International Space Station, at only 400 kilometers, consistently report seeing flashes of light with their eyes closed. Cosmic rays passing directly through their retinas, triggering the visual cortex without photons. Your vision becomes haunted by physics. You cannot stop. Here is the thing that makes all of this genuinely strange. Astronauts come back changed. Not just tired and dehydrated. Changed. In ways that take months and sometimes years to fully manifest. The fluid shift that begins the moment you enter microgravity. Blood and fluid migrating toward the head because there is no gravity pulling it to the legs, causes intracranial pressure to rise, chronically, for the entire duration of a long mission. Scans of astronauts returning from 6-month stays on the ISS show measurable permanent flattening of the optic nerve. The eyeball itself changes shape. Some astronauts come back needing glasses who didn't need them before. The visual cortex rewires. Balance systems recalibrate. Bones lose density at roughly 1% per month, even with 2 hours of daily exercise, because the mechanical loading that normally signals bone cells to rebuild simply isn't present. Muscles atrophy, the heart shrinks. It has to. In microgravity, blood doesn't pool in the lower body, so the heart never has to pump as hard. It gets smaller and weaker. A returning astronaut's cardiovascular system after 6 months in space is measurably closer to that of a sedentary 60-year-old than the elite athlete they were before launch. Scott Kelly spent a year on the ISS. His identical twin, Mark Kelly, stayed on Earth. NASA compared them obsessively.
Scott's telomeres, the protective caps on chromosomes that shorten with age and stress, actually lengthened in space, then rapidly shortened upon return to Earth. His gut microbiome changed composition. Gene expression patterns shifted. Thousands of genes were being read differently after just a year away from Earth's surface.
The body had begun, quietly, to become something else. We think of space as the thing outside the window, the black part, something you look at. But the edge of space begins at your skin. The pressure that keeps your blood in a liquid state, the gravity that keeps your skeleton loaded and your heart working, the magnetic field that deflects the particle radiation currently passing harmlessly through every room you've ever stood in, the atmosphere that filters the ultraviolet light hitting your face right now. All of it. The entire biological contract that makes you possible is a local arrangement. A deal struck between your species and this particular planet at this particular distance from this particular star. Move 36 kilometers straight up, and the deal expires. The question that nobody has fully answered yet is what happens when humans try to sign a new one. Mars has 38% of Earth's gravity, almost no magnetic field, and an atmosphere 100 times thinner than ours. A Mars mission would expose a crew to cumulative radiation doses that currently exceed NASA's own career limits for astronauts. Children conceived in deep space would develop skeletons, cardiovascular systems, and nervous systems under conditions no human skeleton, cardiovascular system, or nervous system has ever experienced. We don't know what that produces. We are, right now, the last generation of humans who will never have to find out.